Okay, so we've talked about momentum and impulse. And so now it's time to talk about one of the major laws in physics, the major laws of the universe in physics, and that's the conservation of momentum. And this one's kind of cool. It's simple. It's very simply stated. Unlike the conservation of energy, you don't have to find out all the different types of energy and work and all that. And it's actually more rigorous than the conservation of energy because you guys have all heard of this equation E equals mc squared. And we learned in the 20th century that energy and mass are equivalent, and so you'll get these situations in particle accelerators where it looks like mass and energy is just disappearing, right? Or energy is not conserved, and we've never found that with conservation momentum. Conservation momentum holds true at all scales. It's an extremely powerful law, and so we're going to use that to look at things, mainly collisions or systems of particles, in relation to each other. But it's an extremely powerful thing, and the ideas come up a lot as you move through physics and science. And so before we get to the conservation of energy, we have to talk about something called the center of mass. And I think we all have a feeling for what center of mass is. But the formal definition of it is the average position of the matter contained within a body or a system. So if you take any object, or actually a system of objects, and you look at how the mass is distributed in it and its position, and you average out all its positions, you'll get one point where there's an average. It's kind of the average position of where all the matter is in the object, and it's what we call the center of mass. You might have done this trick in grade school or something, where to find the center of mass of an object, you can kind of see it over here. To find the center of mass of an object, you take a plumb line and you just let it hang down and you mark a line. And then you rotate around and let the plumb line hang down again and you draw another line. And where they cross is where the center of mass is. And so that's where you can find the center of mass for weird shaped objects. If it's a symmetrical object, then it'll just be literally in the center of the object if the mass is distributed symmetrically. And interestingly, even if it's a system of particles that aren't connected together, you can still define the system as we did over here. You can define the system, you can take the average position of the masses in the system, and you can define a center of mass for the system. And this is an important concept on the AP Physics 1 exam, is this idea of a center of mass of a system, because we can treat the center of mass as a point particle. So say you had a human, a person jumps, right? Like a basketball or something, or a high jump or whatever. They jump. And all that physics we learned about projectile motion, we've kind of seen balls and cannonballs and spheres, right? But if you look at the center of mass of that person, that center of mass will obey the same physics as the projectile motion that we studied, even though their arms and legs may be flying all around, right? The center of mass of that system will follow a nice projectile motion path. And it turns out that with momentum, we can define this conservation of momentum in terms of center of mass. And so one way, and there's a few different ways to define the conservation of momentum, but what this law essentially says is that in the absence of forces external to the system, I'm not sure why it's plural. In the absence of forces external to the system, the momentum of the center of mass of a system will remain constant. Okay, it's a very simple statement, a very simple idea, but essentially is saying the momentum of the system before and the momentum of the system after has to be the same unless it's acted on by a net external force, in which case, if it is, then we would have impulse, we would have a change in momentum. Okay, and so impulse is kind of analogous to work with energy, and momentum, would then be the energy. So, a simple application of this, I was trying to think of some ideas. So, kind of a fun example. I don't know if this one. It's not going to be fun for astronauts. So we have an astronaut floating in space, and oh no, I'm floating away from my spaceship, but this astronaut has a hammer. Okay. Let's see. I'll try to orange, but anyway, they have a hammer, and and they work on the spaceship, and the tether broke or something, right? And say that this astronaut is floating out in space, and it has a velocity of 0 meters per second, and this is the before. Okay, so we'll do kind of before, and we'll do an after. So before, it's 0 meters per second. Maybe the mass of the astronaut would be 100 kilograms. The mass of the hammer would be maybe 1 kilogram, so it's a pretty hefty hammer. 1 kilogram is about like 2.2 pounds. It's a big hammer, right? And they're just flying around space, and the astronaut, maybe his ship is back here, and he goes, oh, I need to get back to my ship. So, knowing physics, what this astronaut does is decide to use the conservation momentum. And now, right now, the momentum of the center of mass is going to be 0. It's going to be 0 kilogram meters per second. Okay? And what the astronaut decides to do is he decides to like throw this. Okay, he's going to throw the hammer out this way. He's going to give it a good throw, and this hammer is going to start traveling away at 10 meters per second. So like a really good throw. So we have this 1 kilogram hammer traveling to the right at 10 meters per second, and we have this 100 kilogram astronaut. And the question is, what's the velocity of the astronaut going to be? So let me go back to my slide here. Okay, so the question is, what's the velocity of the astronaut going to be? So because momentum is a vector, we have to, oh my goodness, this is going to be painful. Because momentum is a vector, we have to define our coordinate system. So we're going to have to maybe say that way is positive. But what we know is that because the center of mass of the system originally had a momentum of 0 kilogram meters per second, then it still has to have a momentum of 0 kilogram meters per second, even after the hammer is thrown, even though those two are not connected anymore. And so what we can say is that if we add the momentum of the astronaut and the momentum of the hammer, they're going to have to add up to be the original center of mass momentum. And so what we'll say is that 1 kilogram, so this is for the hammer, 1 kilogram times 10 meters per second, okay, plus 100 kilograms times whatever the velocity of the astronaut is, will have to equal 0 kilogram meters per second. So the sum of the momenta of all these particles has to add up to be what the momentum of the center of mass is. And do a little algebra, so we'll have 100 kilograms times v, which is equal to negative 1 kilogram times 10 meters per second, or negative 10 kilogram meters per second. We want to solve for v now. So v will be negative 10 kilogram meters per second divided by 100 kilograms. And so we get a velocity of negative 0.1 meters per second. So what this is telling us, it's telling us some cool stuff. It's telling us that the astronaut is going to be going backwards, okay? And he's going to be going backwards at 0.1 meters per second. And in doing so, the center of mass, the momentum of the center of mass of the system will remain the same, okay? So that was a very kind of simple example of a conservation and momentum problem. There's other problems that you can do, other situations, which we will consider in class. So I hope you guys understood it. And if you have any questions, please let me know.